So when we start, if we start with it compressed in this configuration, I started with the 0 being to the right. I could have put the spring on the right-hand side. We could have gone left. But since I started with a spring that's going to oscillate back and forth to the right and then back to the left, my axis that I picked puts that at -5. So then a second later, what are we going to see? Where's our spring going to be just 1 second later? Let's do this. Well, this piece is going to have spread out a little bit, right? So let's make that at -2. So now we're at 2 seconds, -2 meters. And then maybe at 2 seconds, let's see, make another graph here. So for -5 centimeters, 0. So now we're here. T equals 2. Now here's +5. So then we are at 3, 4, see. Whoops. So we're at time equals 2 seconds. Oh, I see what I did. I put the dot in the wrong spot. That's what the problem is. So at 1 second, we were at -2. And at 2 seconds, we were at 0. What's going to happen when we get to 3 seconds? Now it's going to be on the other side, right? It's either going to be at 2 or 3. Let's just make that at 2. So now we're over here. 3 seconds, we're at +2. And at 4 seconds, we're going to be at +5. So we get a graph that looks fairly linear coming up. But what happens when we get to the 5 centimeters on the far right? It's going to start coming back, right? So at this point, it's going to start tracing that path back the other direction. And so our graph is going to look a lot like an absolute value, but not quite so sharp at the top. Why is it not so sharp at the top? There is actually time, right, that passes, and it's going slower and slower at the top. So one of the things that people say, especially when they watch athletes in basketball more so than any other sport, basketball and football, the wide receivers in football and basketball players that are usually trying to dunk, it looks like the person hangs in the air for a little bit. Okay, it looks like they kind of like almost like time slows down and they just float through the air very gracefully, right? Michael Jordan was known for those. LeBron James is known for those. But it's this idea of as they're going up, they're going slower, right? So if you're going slower, it takes more time for you to cover the distance. So where do you spend most of the time in your motion? When you're going slowest. So if we're going slow, where would we go slow? At the far right and the far left. So we're going very, very, very slow, slow down, stop, come back. So it's a gentle turnaround, okay? It's not a hard, sharp bounce off the wall. An absolute value function might be better if I throw a tennis ball at the wall and it bounces back at me, or a super ball on the floor and it bounces back up. That would be closer to an absolute value. This graph, if we do it over time, is going to continue to do this pattern. So what are we going to see? It's going to go back up and they'll go back down. So we get what's called a periodic function. Periodic because it repeats the pattern over and over again. Does that make sense? Which periodic function is this? Is this sine or cosine? This one is going to be cosine function to model. So we're going to use the cosine function to model our path. So as this piece goes in and out, it goes up and down on a position time graph, far out to the left, far out to the right. I'm going to wait there to see if you have any questions. because it's a little weird to think of this as going, you kind of have to think of this piece as if we took the graph and turned it here. And then we move up and up and up and up. And we start coming back down. So if you think about it going sort of a vertical spring, it would go up and down and up and down. Does that kind of help what we got going on there? Okay. So a horizontal spring is a little bit harder to see than a vertical spring, because in a vertical spring, you actually see it go up and down and up and down and up and down, just like the cosine function goes up and down and up and down. Okay. So what is the equation? What is the model we use for this? Well, the model we're going to use for this is a cosine function. And I'm going to scroll up here. So the position versus time. It says position as a function of time is a cosine two pi over capital T times lowercase t. We're going to need to explain all those letters because it's several. And I'll write this up here and then I'll give you time to look and think. 2 times pi is just a constant. Capital T is the period. Little t is the time you measure. So I'll wait right there for just a second. I got to remember to turn in attendance. Hang on for just a second. Let me get attendance turned in. Okay. All right. So A is amplitude. What is amplitude again? How could you describe the amplitude? Okay, it is both of those. It is the maximum displacement from equilibrium. Gonna run out of words, letters. Let's put that on a different line. So maximum displacement from equilibrium. Some of you have had this piece in your math class and some of you have not. When you're working with sine and cosine, the normal period for sine and cosine is 2 pi. But we might have to ratio it with some other number for time, depending on how long or how fast our spring does its thing. So time period would be total time from when? It's the total time to return to where you started, to original position. Get those up a little bit higher. So let's look at how do we use this to graph something. Well, if you have a graphing calculator, basically what you'll do is take your function and fill in all the pieces you know, okay? So in this case, let's say that we know we have a spring whose period is 0.2 seconds and whose maximum displacement is 4 centimeters. Write the position equation as a function of time. So in this problem, they tell us the period and they tell us the amplitude. So this is the nice simple part. So all we have to do is put the right numbers in the right spot. I know some of you are still writing, so I'll wait for just a minute while you get that caught up. But we're going to start with position is a function of time, a cosine, 2 pi over period times time. And then we're just going to fill in what we know, which in this case is the position at some time t would be 4 centimeters, cosine of 2 pi over 0.2 t, and that would be our function. That would be our function. So I could ask questions like this now. Where is the spring at time equals 1 second? Where is the spring at time equals 1 second? Well, let's see. Position at 1 second would be 4 cosines of 2 pi over 0.2 times 1 second, which gives me 4 cosines of 2 pi over 0.2. And when I fill that into my trusty calculator, should be the cosine of 10 pi. So we get 4 times the cosine of 2 pi. Make sure you put 2 pi in parentheses, because if you don't, it may do something you don't anticipate. So it would be at 3.4 centimeters. So if it's at 3.4 centimeters, can I determine which way it's moving? Or do I have to have more information to know something about its velocity?
Well, wouldn't you be able to tell it's like moving to the right because it's positive?
Okay, so if the position is positive, let's go back up to this. If our position is positive, that means we're to the right of equilibrium, right? Do you only move to the right when you pass equilibrium? No, you move out to the right and then it comes back to the left. So we're going to have at least one more piece of information to be able to tell which way this thing is moving. It may be moving out to that furthest position, or it may move out and be coming back. We don't know. We do know it's to the right of equilibrium, so the spring would be extended in our case. So what other piece of information would help us to know if it's moving to the right or to the left? Frequency, what does frequency tell us?
Tells you how many oscillations per second.
How many oscillations per second? So if I know that how would I use frequency to get to my oscillation number?
Well, if you know how long it takes to
Okay, if we know how long it takes to take a total path, then we might be in business, right? Okay, so let's ask that question. What is the frequency of our movement? Remember, frequency tells me how many complete paths I get in 1 second. So let's see, what is our period? Well, period equals 1 over frequency. So 0.2 equals 1 over F. So F equals 1 divided by 0.2, which is 5 seconds. 5 seconds. Or sorry, not 5 seconds, 5 hertz. What am I doing? Losing my mind. Hertz. Hertz is no number on top, but no unit on top, but seconds on the bottom. So we get 5. The way you think about this is 5 patterns in 1 second. We call this unit the hertz, just like the rental car. It is seconds to the -1. So hertz. So our little guy is going to do 5 back and forths in 1 second. So if I've only gone 1 second, what does that probably mean?
You've done 1 pattern. 1 second, so you've done 5.
If I've done 1 second,
You've done 5.
I've done 5 patterns. So am I moving out towards the amplitude, or am I moving back towards equilibrium? So what I did was I started in, right? I went all the way out, all the way back. 1, 2, 3, 4, 5, and I did all of that in
1 second.
1 second. So in 1 second, that shows me at 3.4. So what is the most likely thing for me to be doing? Finishing up at, right? I get 5 whole ones in 1 second. So it's most likely that I'm moving out towards an amplitude. I'm finishing the last bit of the pattern. Does that make sense? Now, I would suggest that you find out how long it takes to get to equilibrium, and then you'll know one way or the other. But if you have a graph, it's a little easier to deal with. So we're going to let that go for just a second. We'll come back and think about that some more. So let's ask one more thing here. Let's say it like this. Through what distance has the mass traveled after one oscillation. So if we were to just add this as distance instead of doing displacement, how far will this mass have actually gone? So your idea here is I go out and I come all the way back for one oscillation. So how far has the mass actually traveled? It has gone, let's go back up to our picture. Yeah, I hear you. We've gone all the way out here and we've come all the way back there. Each one of those paths would be what? In this case, 2 amplitudes or 10 centimeters for this one. So what would it be on the one we're working with? It's going to be 8 across, right? And 8 back. So this will be 16 centimeters. Okay, so on this, your calculator should be in radians. Oh, yes. Okay. Yeah, we should get 4. I set it up. Okay, so yeah, thank you for that. We're back in radians now. My fault. We've been doing degrees all year. So this would put it at 4 centimeters. Straight up. Because it'd be 10 pi. 10 pi would put you back at where you started. So all year we've used degrees, but when we start doing this, we have to use radians. My bad, because we're using trig functions. Oy. Yes, yes, we have our moments. Okay, so 5 hertz, 4 centimeters. All righty. And 16 centimeters, why is it 16 and not 8? Because you have to go from where you start all the way to the other amplitude, which is really 2 amplitudes on the way out and 2 amplitudes on the way in. So you travel through a distance of 4 amplitudes for every oscillation. 4 amplitudes for every oscillation. For every oscillation. Okay. I'm going to wait. Any distance learning kids, if you have questions, please feel free to unmute and ask, or just put them in the chat box. That was a lot. We're gonna do some problems now. But I'll wait for just a minute. If anybody else has questions in here. Okay. All right. So going to whoops. All right. So a couple of other things. Last bit of notes on this. What if we want to know the velocity time function? So we've got position time is a cosine function. And I'm gonna move this over a little bit. So what is our velocity function going to be? And let's talk quickly about this really quick like. We'll look at the maximum values. We call these degenerate cases in math. I know that degenerate is not always used the original sense of the word, but a degenerate case in math is sort of the maximum or minimum condition. It's the worst case possible, if you like. But for us, what is the maximum value? Well, let's talk about this function for just a second. What is the biggest value that cosine could ever be? The maximum value of cosine is plus or minus 1. The minimum would be -1. The maximum would be +1. Because the cosine function always gives you a ratio. Always gives you a fraction. It's the adjacent leg of your triangle to the hypotenuse of your triangle, which I know makes no sense in this context because we're not working with triangles. But we do move in this kind of cosine pattern, so this is the model that fit best. So if the maximum value is positive or -1, what is your maximum displacement? Which is why we call that the amplitude. It's the maximum displacement. So what is our velocity time graph going to be? I have some people in here that are in calculus. Yes? A few here, there. I know Nathan is. Anybody else? Hunter, are you in there? Okay. Connor?
Graduated, well, two graduated last year.
Last year. Okay. So what is velocity again? Let's go back to the very beginning. What's velocity? What's the definition of velocity? Speed in a direction. And how do we calculate speed? Back from 4th grade or whenever you first learned how to do speed. Distance divided by time. So velocity is your change in position over your change in time. Just to refresh that from earlier in the year. So my calculus children, help the other ones out. That's a derivative, is it not? So dx dt. If you don't know calculus, you don't have to know this. It's we won't use it at all other than just to connect it for them. So if it's a derivative, what function should I get here? Do the chain rule.
I have an answer.
Nathan has an answer. You have to do the chain rule. Who's your variable? Nathan, go ahead. Who's the variable here?
Variable is t.
Little t.
Little t.
So what is the derivative?
You're asking me again?
Yeah, go ahead.
It's negative a 2 pi t times the sine of 2 pi t times t.
It looks better in rotational form. It looks ugly in linear form. Ooh, so if we start with a cosine function here, we get a sine function here. So what would be the degenerate case? What is the maximum value of sine? What's the biggest sine ever gets? Also 1 or -1, which means what's our maximum velocity? Almost. Yep. And for those of you keeping score at home, so what do you suppose that our acceleration function is going to be? Hey, it's a derivative too, because it's changing velocity over change in time. We get negative a pi over t squared. Back to cosine. So max value. Cosine's biggest value is 1. So this is 2 pi t over t squared. That looks like a lot of symbology. Okay. I know there's a lot of letters and stuff floating around up there. A lot of numbers and stuff floating around there. It looks scary and it looks hard, but mostly you only ever use the first function and the maximum values for the other two. And we'll have a better way that's prettier to write this later. When we do rotational stuff, there'll be a better way to write this. Still be the same ideas, just prettier looking. Except it uses Greek, so maybe if you don't like Greek, then it won't be prettier looking. We ran out of English letters. True story. Ran out of English letters, so we have to use Greek. You may wonder why we don't use Latin. Oh, that's right. Our language is Latin. You've probably seen the meme that goes around that says we should change, what is it? Change Arabic. We need to change our Arabic numerals back to European numerals. Who wants to make us stop using Arabic numeration in schools? Nobody, because the Arabic numbers are our numbers. I want to change from 1, 2, 3, 4, 5 to something else. Sure as heck don't want to go back to Latin. Although writing 2000 something is way easier than like 1939. Right?
They do math like this in Roman.
Yeah. As one of my friends said out in a tweet last week, Newton was so bored during the plague, he invented calculus. Kind of true. He was home due to the Black Plague on his parents' apple farm. His parents owned a farm and they had apple orchards and peach orchards and stuff like that. That's where the apple dropping from the tree story comes from. But he was actually at Oxford in college when the Black Plague hit. And so obviously if you had money and a way to get out, you got out. You didn't stay there with all the dying people in the plague. So he went home and then he had all this time to think and do, and he invented calculus. And a lot of the physics we're going to do in physics 2 this week, starting this week, optics. Yeah, I don't think I've ever been that bored. I love calculus though. Calculus is fun. So here's what I want to tell you. Back to this. What is the fast? Let's get back to this. This is the one you're going to have to be able to work with. These other two, we usually just use these maximum values. And right now, we're not going to spend a lot of time on that. I just kind of want to preview it for days to come. Okay? So let's look at, let me pull this up real quick. Because AP does not ask a lot of mathematical questions. AP asks a lot of explanation questions. Okay, so just a second, let me pull this up. Let's see if we can't wander our way into a solution here. Here we go. I'm gonna put this problem up. This is what your homework problems are going to look like. And on Wednesday, we may do some examples. So here's our cute little problem. Actually, let me shrink it down just a little bit. Go like, okay, so that we can all see our picture. So a car is attached to a spring, displaced from equilibrium and released. There is no friction. Hallelujah. The graph of the velocity versus time is shown. The arrows and signs above the cart indicate the positive and negative directions for the position of the cart. Okay. So this is a graph of speed versus time, yes? So let's start looking at what does that do for us. And I'm going to pull up my, well, I say I'm going to pull it up. Come on, Word. Play with us. Let's see if we can't figure out what's going on here. These kinds of questions. So we called left negative and right positive, shockingly. We get that from the picture over here in this corner. Don't you even do it. Okay. So what is the period of motion for this car? Explain your reasoning. Going to give you time to think. Feel free to discuss with the people around you. So you can look at each other and tell each other what you think, but you might want to think first. I'm going to get some caffeine. It's that day.
So how much time takes to get to the original position? It doesn't go back to the original position. So four.
I'm going to go with the tea version of caffeine rather than the Mountain Dew version.
Yeah.
You guys can chat with each other too if you want to. That works pretty good. If this was a position time graph, if we had position time graph or location graph instead of velocity time, what would we be looking for? We have a position time graph, the thing that maps where our car is at any moment. What would we look for to find the period? Because remember, period is a time. What would we look like for on a position time graph? Say it louder. An x-intercept? When it returns to its initial position, is that what you said, Connor?
When it aligns with the original position.
When it aligns to its original position. What is a period again? The amount of time it takes, it's time. The amount of time it takes to go back to where it started. So if I had a position time graph, I could just pick any position and look at the graph until I got back to that exact same spot. So if this was position time, I might look here and then look here and go, the period is 8 seconds. If this is position time, I would say the period is 8 seconds because I started at 0 and I went up and went down and came back. After 8 seconds, I'm back where I started, moving in the same way. Or maybe Autumn wants to start here at 4. She could go 4 to 12, right? Once again, 8 seconds. However, this is not position time. It's not position time. So what does it mean to get back to where we started in terms of velocity? Ooh, looks like this is going to be the brain teaser for tomorrow. Let you think about that. The bell's fixing to ring. We're fixing to go to impact time. I'll let you think about this one. This is going to be your challenge, and we'll start there tomorrow. Yeah. Or not tomorrow. Don't come tomorrow. Tomorrow's election day. Come Wednesday, where you will get the answer to this question. And if you have to go to impact, have at it.
So do any distance learners have Zoom calls for tomorrow then? Or no?
No, because it's election day, so everybody's off work.
Okay.
Yep, y'all too. So y'all don't check in or anything tomorrow with any of your classes.
Are the teachers still gonna like give us homework?
I don't know what your teacher's gonna do. This teacher just gave you some homework, but you may not be able to do it until Wednesday, and that's okay. You can finish up the labs and such.
Ms. Wilson, I need to go, but I'd like to check some.
Okay, yeah.
This
So you
is-
guys are free to go or stay, whatever you want to do and ask questions. I got to check with Nathan. Which ones?
This is 1989 M2.
1989 M2. Oh. Just open it. It's still where it's always been, you goofus. Some days, me and my computer. 1988, oh yes, the Atwood machine.
Yes.
1989. There it is. Okay, so you should have for letter A, sum of the forces is 2mg minus TV. So you get 2m times g minus a quantity, or 2mg minus 2ma for part A.
Perfect.
B, the torque is 3mr squared times a over r. So you end up with 2mg minus 5ma.
Okay, I made a mistake somewhere there.
Okay.
It's like
C,
a 3 in that.
okay. So C is
Well, I
C.
know my answer for C is wrong because I used my answer. for
Right. Right. Okay. You should have gotten, ooh, I don't know. I don't know that I can do that one backwards to check where you're, like if yours was right. Mu should be about 0.1 if you want to just write that down so you'll have it to check tomorrow or Wednesday.
Wait, so they got an actual answer for it?
Yes.
Okay.
Okay, so yeah. And then D should be the acceleration centripetal is about 1 meter per second squared.
Okay, I didn't get to.
Okay, so we lost it somewhere on B.
Yep.
And then we'll have to go back and find it. Okay, we can do that Wednesday.
Perfect.
All right, have fun.
Alright. So Connor, when will we know if we're performing or not?
Probably by the end of the day. Probably.
Probably, most likely, maybe.
Well, it's Mr. Router, so it's really 50-50.
I love him. He's funny. Yeah.
A little above my pay grade.
Okay.
I don't do calculus, but how do we get an exponent higher when we took the derivative of velocity?
Because when you take the chain rule, okay, so the derivative here, you have a function cosine, and inside that you have a function. You got two functions, so you take the derivative of the outside function times the derivative of the inside function. This is just a constant, so that just stayed out in front. Derivative cosine is negative sine of the same stuff. And then the derivative of the inside is this, because that's just a constant in front of t. When you do that again, you get another one. So when I take the derivative of this mess, this is just a number. The derivative of negative sine is positive, is negative cosine of this, times the derivative of the inside, which is another one of these terms comes out. So then you have
So
the
it's
two.
squared.
So it's a chain rule. Yeah.
Okay.
Yep. How's it going?
Here.
That movie came out when I was in 6th grade. Top Gun did.
Yeah, I wasn't alive
Yeah, I know.
yet.
Y'all weren't alive when I was at Washington DC when the Pentagon got hit by the plane either. Field trip with students. Huh? Some of you were, yes. Some of you were not.
I was not.
It was 2011 or 2001, sorry.
No, that's South Sudan.
9/11/01. Yeah. How's it going, Emily? I saw you got your quiz taken. Sorry about that. Yeah. Yeah, I haven't graded y'all's quizzes yet. That's on my list to do next period. One should have a key before one tries to grade it. We had 2 last week, didn't we? So probably both of them. Okay. Then one of them, I have a checklist. My checklist tells me what I've got to do. The only way I know what's going on in my life. I used to have 3 day planners. Back when I still coached basketball and softball, there was like the basketball, softball day planner. and the school day planner and the real life day planner, you know, so that your water wouldn't get cut off because you forgot to pay your water bill for 2 weeks. Not that that's ever happened to me 3 times. Softball season sucks. Just gonna say. Because you play Monday, Tuesday, Thursday, Friday, Saturday. If you win in the tournament that was on Saturday, then you play Sunday. And on Wednesday, you sleep.
Yeah, I have practices Monday, Tuesday, Wednesday, Thursday,
Mhm.
competition Saturday, state church, 20 Sunday.
Yep. We're only still doing one church on Sundays and one Zoom in church. They videotape it and put it on YouTube.
I like regular church and then I do group Wednesday day.
I didn't realize, and it doesn't matter, but I didn't realize how much more time people that don't go to church have on Sundays. Like until we got into this, and I'm like, now I see why people don't go to church. You have like this much more time. Not that that's a good plan, because we always say the banana that leaves the bunch gets peeled.
That's dark.
Yeah, well, if you don't go hang out with your Christian friends, sometimes you can get peeled away from the group. But yeah, the banana that leaves the bunch always gets peeled. I had my course director in high school who I loved and I still love, and the bozo is still teaching. I didn't realize how much younger he was than we all thought he was, because you know your teachers, you're just kind of assume they're ancient. But he was amazing, but he would tell he had gallows sense of humor. And so some of us picked that up, and I kind of had that anyway, because I've got a lot of military people in my family. So I tend to go with the darker jokes on some of those things. I asked last year's class if they remembered the period of time, because almost every kid, you go through the poo-poo and pee-pee jokes as a kid. Everybody goes through that. But there for a while in my class, we went through the, hang on just a second. Jackson, you need something?
No, I'm good. I was just about to leave.